I think I'm going to lay it on the back of Ringling Brothers and Barnum and Bailey Circus. I think it's P.T. Barnum that said that one.
Yeah, actually.
Okay. On Friday, I was talking about the normal vector to a surface. And we had our normal vector going in a couple of different options. And we came up with these calculation versions. And in the surface given by a graph, I am absolutely sure that this vector points up. And I look at this and I realize there's a typo. It's not a huge typo, but it's a typo. Because this is an I and a J, this should be 1K, not just 1. That way I'm sure it's pointing in the up direction because the Z component is positive. With the RU cross RV, I don't know that that normal surface vector is always up. But I can arrange it so it is always out. And on a closed surface, that's actually what's important. So on page 1128, we see a closed surface with an outward positive orientation and an inward negative orientation. So again, just like I had a curve with an orientation on it, and I have an orientation for a surface, but it doesn't tell me which way I'm going, very much like a plane, it tells me which way I'm not going. And I want out to be the positive direction. The reason I want to do that is I want to talk today about the way we integrate vector fields with surface. This is what we were doing with line integrals with Green's theorem. I was integrating a vector field with respect to the curve. So this is my goal here. I really want to figure out how to integrate across a surface. So let's imagine for a moment, I have this surface. I've got a nice orientation on it. It's oriented upwards. Now let's imagine that this is in some vector field. I can picture it like it's a net, and I've got this stuck in some water. And there's a water fluid of some type moving with a velocity. So I've got fluid with density, rho, and velocity, v as a vector, flowing through my surface S. Right? What I want to measure is the amount of fluid crossing some little square. Here's a little square. We'll call that the area. We'll call that the IJ square. Hey, wait a minute. Like we broke it up like a surface into little squares. So I have SJ, this little square within my surface. My question to you, how much fluid goes through Sij? You actually do know the answer to it. If you just think of the fluid as a vector. Well, the amount of that vector would depend on its angle relative to the normal vector. Stuff that's going this way, perpendicular to the normal vector, isn't going to go through S at all, is it? Stuff that's going at an angle up or an angle down, only part of it will go through. So if we consider the vector for the fluid, to be a different vector, say pointed in this direction for the moment, how much of that is going in the same direction as n? And that would come from a dot product, wouldn't it? So I can do a dot product. I can take the fluid dot the normal vector. But wait a minute, our fluid has density v and velocity F, so I'm going to write that that fluid vector as density rho times the velocity v, and then I'll take the dot product with n. Now that would tell me how much is going right at that one spot. I'm going to have to say that that's multiplied by the area of that little square, so I get the amount for that square. Hey, wait a minute. Wait a minute. That's just through that one little square. I want to know the total. What do I do? Sum them up. And if I sum them up, that becomes an integral, doesn't it? But it's an integral using the surface area, which means it's an integral ds. The integral over the surface S of f dot n with respect to S, surface area. A lot of people will abbreviate this and write this f dot ds with a vector on it. I hate that. It makes me crazy. I understand why they do it. I just don't like it. I'm going to write f dot n ds almost all the time. We're going to call this, wait a minute, I'm thinking about how much goes across this. We're going to call this flux. We're either going to say through S or across S, depending on which book you're looking at. You'll see both terms. Another way to phrase this is the surface integral of F over S. Right? I wrote that back up here at the top where I wrote the surface integral of a field over S. That's this same idea. Hey, wait a second. Let me look at an example, a general one. I want to know what happens if my surface is given by a graph. Well, if my surface is given by a graph, z equals g of xy, then what's my normal vector? This is what I was just talking about at the very beginning of the class today. I said there was a typo in it. You made the correction in your notes from last time. What's our normal vector? Okay, so there's my n. Let me suppose, in addition, that my vector field is PQR, just like a typical vector field is. Yes? Now I want to do this flux integral. Then the flux is double integral f dot n ds over the surface S. But F is PQR. And I'm dotting that with this. And then I need the ds part, right? What's ds when I have a graph? There. There's a little bit more. Aha. Which means these cancel. And all I have to do is the dot product. Wait a minute. When I do the dot product, I multiply the I part by the I part, the J part by the J part, and the K part by the K part. So I get negative P times GX minus Q times GY plus R. The square root cancels with the square root. That's done dA. Holy crap, wait a second. That looks familiar. Remember we did F dot dr and we had PDX and QDY. Well, there's the dx and the dy part. Only I'm on this surface, not in the xy plane, so that bends because of the g. This looks exactly like the surface idea of the line integral we did for Green's theorem. These look very similar to me. Because that measured how much we were going in the x direction, that measured how much we were going in the y direction. This measures how much we go along g in the x direction, measures how much we go along g in the y direction, and the fact that our normal vector is oriented up is where those minus signs come from, just like they did in the equation of the tangent. Holy crap. I think I like this formula just a little. But this is only one of the two options. This is only going to work when my surface S is the graph of something. There was another option. What was the other option? Okay. Sorry, I started to write the wrong thing. Then S is some function R of UV, right? So I have two questions. What is the normal vector in this case? And what is ds in this case? Now, again, we've already worked these items out. What's my normal vector? What's ds? Hey, wait a minute. I'm going to do f dot n ds, right? The double integral over the surface of f dot n ds. What happens when I do n times ds? Yay! My integrals just got simpler when I do flux in either a graph or a parametric setting. The actual surface integral is easier than the generalized surface integral. Okay, physics 2 people, capacitance, Gauss's law, electric behavior on a surface is exactly this idea. When you are measuring capacitance, you're looking at the difference between two surfaces of how the electrical behavior is going on. You're looking at the field from one surface to another. Flux is a measure of how the field crosses the area in between. Capacitance quantifies that. Gauss's law measures. I put in your hands the ability to control electricity, or at least to measure it at the moment, so we can figure out how to control it. Told you I'd make it up. But if these integrals look like Green's theorem, then I want to do Green's theorem. Well, the advantage is that I'm not going to do this. I'm going to find somebody who already did it and tell you about it. But here's a motivating example. Suppose my vector field is going straight up. I'm going to do the surface integral, the flux. I want to find the flux through the upper hemisphere of the unit ball. Wait a minute. That's a function. What's the graph z equals for the upper half of the unit sphere? That's the radius for that circle, right? You're close though. What's the equation for the sphere? That's a circle. I need z squared in there, right? And the radius is 1. So when I solve that for z, I get z squared is 1 minus x squared minus y squared. So I take the square root, right? Now, that means I know my normal vector. N is partial with respect to x with a negative sign times I, minus partial sign with respect to y, negative sign times j, plus 1k over square root of zx squared plus zy squared plus 1. I used z instead of g because I didn't write my function as g of xy. I wrote it as z of xy. But wait a second. I'm doing the double integral of f dot n ds, right? Over this surface. According to the equation we just wrote down with a giant big star next to it. That's that underlined piece, the double integral over d minus pgzx minus qzy plus r. Well, now I've got a question for you. Since I am integrating over a domain in the xy plane, what is d? Where does my surface live in the xy plane? Not just on the circle, but inside the circle as well, right? So that's what I'm integrating on here. Wait, here's f, right? F, what's p? And q and r. Which is a constant. What just happened to my integral? It became the integral over the circle of 0, 0 plus v0 dA. Wait a minute, that's a constant. When you get a constant, you could do this integral over the circle in polar coordinates, right? But when you integrate a constant, it's a number times 1. The integral of 1 dA is the area of D. What's the area of that circle? R is, so that's just pi. Ta-da! That was really nice. So I was able to do this surface integral fairly easily. I'm okay with that. I want to do it again on a different surface. Instead of doing the upper hemisphere, I'm just going to look at the disk in the plane. In other words, this time, I'm actually integrating there. My surface is just a disk. First question for you. If that's my surface, where's the normal vector pointing? Straight up. Which means a unit normal vector is what vector? Because we're going straight up. Oh, so now I'm going to do the integral of f dot n ds over this surface. I'm going to do it the same way we did right up here. Wait a minute. 0, 0, v0 dot 0, 0, 1 dA. What's that dot product? Isn't that the same integral? How, why? Well, A, it's because I rigged the hell out of this problem, but it cheated. What do these two surfaces have in common? So here's my crappy picture of that surface, right? And S2 where's S2? Which means they have the same edge. The boundary of the first surface is the same as the boundary of the second surface. Imagine if I gave you an open cylinder. Take your Contigo, which I'm assuming is the other one. Is that empty? Oh, okay, then I'm not going to ask you to do it. Take that, take the lid off, turn it upside down. The circle would be in the XY plane, wouldn't it? If I did the flux on that, it'd be the same thing. Wait a second here. if I think of the edge of this as a positively oriented curve, what does it mean to be positively oriented as a curve? That's for a surface. Surfaces, it points out. What's it mean for a curve? Faces the inside. So I'm going positively oriented means counterclockwise. So if I pictured myself walking counterclockwise along this circle or along that circle, my left hand would be in, right? In the bottom picture, I'd just be pointing into the XY plane. If I was walking around the upper surface, I'd be pointing up onto the surface of the sphere somewhere, right? But I'd be pointing into the region as I walk around the edge. If I think of these as positively oriented boundary curves, then I can use Green's theorem. Only I'm not going to use Green's theorem flat. I'm going to use Green's theorem on the surface itself. And the generalization of Green's theorem is called Stokes' theorem. Actually, the apostrophe goes on the end because his last name is Stokes. Stokes' theorem, let S be a oriented piecewise smooth surface bounded by a simple piecewise smooth closed curve C with positive orientation. So I've got a surface. The word piecewise smooth here means consider that upside down contigo. Notice that the edge where the side meets the top, that would be a sharp corner, wouldn't it? But I could think of the side and the top as two smooth surfaces with just that one little edge difference. And that's okay. I'm allowed to have edges, just as long as they're not everywhere. Let F be a C1 vector field in a region containing S and C. I need my vector field to be continuous and continuous in the first derivative. Then the double integral over the surface. I'm going to do the flux. I'm not just going to do any flux. I'm going to do the flux of the curl of F dot N. That's the flux, not of F, but the flux of its curl. That turns out to be equal to the integral of F dot dr. This is the line integral we did for Green's theorem, right? Curl. Qx minus Py was part of the curl, wasn't it? That's the double integral we did for Green's theorem. This is Green's theorem. Moves from 2D to 3D. By the way, we also wrote this as F dot T ds So you may see it written that way as well, but I tend to use the F.dr. Holy crap. I can move Green's theorem from 2D to 3D. As long as I put the right orientation on the boundary curve. I did say closed, so these should be closed path integrals. Now, why would I do this psychotic sort of to you? Just like with Green's theorem, it's a matter of which one of these is easier. Is it easier to do the surface integral, or is it easier to do the line integral? And if the curve we are describing is kind of hard to deal with, maybe it's going to be hard to get a parametric representation. Then I don't want to do that. But if the curl turns out to be nicer, we'll do that. Let me do an example. I beg your pardon. The hell is this? This is gross. But let me think about this. My curve is the intersection of a cylinder and a plane, right? Let's draw this setup. Okay, I'm going to draw the surfaces. X squared plus y squared equals 1. What's that surface look like? The cylinder of radius 1. Perfect. And then equation, new equation, z equals, wait a minute, it's y plus z equals 2. Y plus z equals 2. What's that equation look like? And it's a plane, z equals 2 minus y, so it's slanted that way. I'm going to change the color on that just so I can tell the two of them apart. Let's make that one red. There we go. Great. So the curve I want is this kind of angled ellipse here. You know a set of parametric equations for that? We could figure one out, right? Let's see. I'm on the cylinder, right? That means I can think of this ellipse as if it was a circle lifted up. What are the parametric equations for the circle? Okay, so x is cosine, y is sine, radius is 1. I'm good with that. So I can say right here, x equals cosine theta, y equals sine theta, 0 less than or equal to theta less than or equal to 2 pi. How do I lift that to give me the z? By the way, exam 1, the last question on the first exam, asked you to lift a curve onto a cone. Promise, you've done this before. It was just a long time ago and I've forgotten it. How do I lift that up onto this surface? Y plus z equals 2 means z equals 2 minus y. So that's 2 minus sine theta. So I actually have r of theta. Cosine theta, sine theta, 2 minus sine theta. But now I got to do f. And f has to be done with these things. So f is now minus y squared minus sine squared theta, x cosine theta, z squared, 2 minus sine theta squared. And I'm going to do the integral of f dot dr. That's the integral of minus sine squared theta, comma, cosine theta, comma, 2 minus sine theta quantity squared dot dr. Derivative of cosine is minus sine. Derivative of sine is cosine. I'm going to run out of room here. Derivative of 2 minus sine theta. Derivative of minus sine theta is minus cosine theta d theta from 0 to 2 pi. I can do this, but this is a trig integral nightmare. Doesn't this just suck? I don't want to do this. Stokes' theorem says I don't have to. Stokes' theorem. It's on this side, I think. That's the formula right there. That's the one he put on one leg. The other one is the one we'll do Friday. Okay. Okay. Two questions. What's the surface S? Let's go back to our picture. What's the surface S? The thing that's bounded by our ellipse. That would be the part of this red plane that's inside the circle. Yes? That's given by an equation. What's the equation for the plane? Or z equals y, 2 minus y. That's a graph. Z equals. Great. Wait a minute. That means here, I can go back and I can say S, z equals 2 minus y over the circle x squared plus y squared less than or equal to 1. That means that this is my domain D. Okay, wait a minute. If I'm doing this as z and I'm doing this double integral, I need zx and zy. What's zx? What's zy? Great. Now I only need one other thing. I need the curl of f. How do I do the curl of f? Curl is of y minus that no, that's the actual result of the integral. But there's a faster way to do it. Yes, that's the equation, but what's the faster way to do it? Now I need f. Wait a minute, I wrote down f. F is minus y squared x z squared. So let's do that cross product. The derivative with respect to y of z squared, the derivative with respect to z of x, minus something j, the derivative with respect to x of z squared, the derivative with respect to z of y squared, plus something k, the derivative with respect to x of x, the derivative with respect to y of minus y squared. But I'm already subtracting, so that becomes plus 2y, because it's AD minus BC. Ah. And now I use that formula we just wrote down with the star on it. P times Zx. Well, P is 0. Zx is also 0. Minus Q, which is 0, times Zy, which is -1, plus R, 1 plus 2y, dA. What's our domain D? Which means I'm going to do this integral how? In polar. Equals the integral from 0 to 2 pi, integral from 0 to 1 plus 2r sine theta r dr d theta. I know how to do this. I know how to do this. Instead of having to do an ugly ass, really difficult line integral, I do a nicer circle. I have this vector field in my picture, which I didn't draw for you yet. But I think about this vector field swirling around, right? And some of it is going to go through that ellipse hanging in midair. Instead of figuring out around what's going on, curl through that vector field. And that gives me the same result. So in this case, doing the double integral was easier than doing the line integral, because I would have had to do way too much trig to do the line integral. But this, I do with respect to theta once. A lot easier. More on this on Wednesday. I'll finish this one out. I'll draw the vector field, and we'll go from there. There should be one where we do it the other way. I'll show you that one as well. See you all on Wednesday.